In this video, we're going to take another look at permutations, and we will introduce a new notation for permutations, which turns out to be especially easy to work with once you get used to it. Let's begin with an example. So I'm letting sigma be the permutation you see on the screen here. It's in matrix notation. It's an element of S sub 7, and it's a permutation of the numbers, the integers 1 through 7. Sigma of 1 is 7, sigma of 2 is 3, and so on. You remember how the matrix notation for permutations works. And we want to begin with a picture of sigma. Here's a picture that describes sigma fairly well. Looking at the matrix notation for sigma, we see 1 is sent to 7. That's represented in this picture by an arrow from 1 to 7. Looking again at the matrix notation, 7 is sent to 4. So in the picture we have an arrow from 7 to 4. And 4 is sent to 1, looking here at the matrix notation. So in the picture, that's represented by an arrow from 4 to 1. This is one cycle determined by sigma. And now let's try starting with 2. Looking at the matrix notation, 2 is sent to 3. So we have an arrow from 2 to 3 in the picture of sigma. Sigma of 3 is 6. We have an arrow from 3 to 6. Sigma of 6 is 5, an arrow from 6 to 5, and sigma of 5 is 2. So we have an arrow from 5 to 2. And that completes a second, what we're going to call cycle, a second cycle in the picture of sigma. So what we see is that the domain of sigma, the numbers 1 through 7, is divided into 2 subsets, each of which is permuted in a cycle to form a closed chain. 1, 7, 4, 1, 2, 3, 6, 5, 2. And as we will see shortly, every permutation can be decomposed like this into cycles. First, we need to say exactly what a cycle is. So if you take distinct elements a1 through a sub k of the set of numbers, a set of positive integers 1 through n, so a1, a2, and so on through a sub k are all elements of this set, and they're all different. Then left parenthesis a1, a2, comma, and so on out through a sub k is shorthand for the permutation of sigma, for the permutation of the set 1 through n, which is described by this picture. Right, the first number in the cycle, a1, is followed by a2. So if we call this permutation alpha, alpha of a1 is a2. a2 is sent to the next number in this k-tuple, a3, and so on. The second to last number in this k-tuple is sent to a sub k, and alpha of a sub k is a sub 1. So this notation, this k-tuple, a1, a2, and so on through a sub k, is shorthand for this picture of a cycle. And if you have a number between 1 and n that's not one of the a's, then alpha of that number is that number. So the permutation described by this notation, left parenthesis a1, a2, and so on through a sub k, sends A1 to A2, A2 to A3, and so on. A sub k minus 1 is sent to A sub k, and A sub k is sent to A sub 1. And any number between 1 and n not appearing here is sent to itself. This is called a cycle of length k. So let's work in S7 for a little bit. These are permutations of the integers 1 through 7. Here is a cycle of length 5. I'm calling it alpha 1, shorthand. So this is a cycle of length 5. It's an element of S7. Alpha of 2 is 3, because 3 follows 2 in the cycle notation. Alpha of 3 is 5, because 5 follows 3. Alpha of 5 is 4. Alpha of 4 is 1. And alpha of 1 is 2. So this notation, this 5-tuple of numbers, describes the permutation defined by these 4 equations. And since we're working in S7, alpha of 6 is 6, and alpha of 7 is 7, because neither 6 nor 7 appears as a number in the cycle notation. So we can see from this example that there is a slight flaw in the cycle notation. You can't tell just looking at this 5-tuple that alpha 1 is in S7. You really have to be told that it's in S7. Without being told which S sub n alpha is in, it could be an alpha sub n for any n greater than or equal to 5. Okay, now we're looking at alpha 1. This is alpha 1, the cycle 2, 3, 5, 4, 1 that we just looked at. Let's try writing alpha 1 using matrix notation. This is something we cannot do unless we know which S sub n alpha 1 is in. Alpha 1 we know is in S sub 7, so the matrix will have the numbers 1 through 7 in the top row. And now we have just used the cycle to calculate alpha of 1. Right, the last number in the cycle is sent to the first. Alpha of 1 is 2. Alpha of 2 is 3. Alpha of 3 is 5. And so on, as we noted in the last slide. And because 6 and 7 do not appear as numbers in the cycle notation, 6 is sent to 6 and 7 is sent to itself also. Let's try a second example. Here's alpha 2. We're still working in S7. This is a cycle of length 6. What about finding alpha sub 2 of 6? You locate 6 in the cycle. The number that follows it is alpha of 6. Alpha sub 2 of 6 is 3. Let's write alpha 2 using matrix notation. So we know we're in S sub 7. We had to be told that, and we were. So the top row of the matrix notation consists of the numbers 1 through 7. And then we just look at the cycle to determine the numbers in the bottom row. Right, so in this cycle, 6 follows 1, so alpha of 1 is 6. 1 follows 2, so alpha of 2 is 1. 4 follows 3. Well, actually 3 is the last element of the cycle. And according to the way the cycle notation works, 3 is sent to 4. So 3 is below 4 in the matrix notation, and so on. Since the number 5 does not appear in the cycle notation, 5 is sent to 5. Alpha 2 of 5 is 5. And now, how many ways can we write alpha 2 as a cycle? This is one possibility. You can write alpha 2 as a cycle starting with 4. But you can actually write a cycle starting with any one of the numbers occurring in the cycle. There are 6 ways of writing this alpha 2 as a cycle. You can start a cycle with any one of the 6 numbers that appears here. So in this list I've started with the original notation for alpha, but we could start the cycle with 1. Right, according to the original cycle, 1 is sent to 6, 6 to 3, 3 to 4, 4 to 7, 7 to 2, and 7 to 1. So we put the numbers in the order I just mentioned in a cycle starting with 1, and we get a second way of writing that same cycle. Or you could start with 2. Or you could start with 3, and so on. You can start the cycle. You can get cycle notation giving you the same permutation starting with any one of the 6 numbers that appear in the cycle. It's customary, but certainly not required, customary to write a cycle so that it starts with the smallest number occurring in the cycle. I didn't do that in my original cycle notation for alpha 2. Here is the way of writing alpha sub 2 starting with the number 1. This would be the customary way of doing things, but you don't have to, and we won't worry too much about doing that. Okay, let's try multiplying a couple of cycles. So we're multiplying the cycle 1, 2, 5, 3 by the cycle 5, 1, 6. These are both cycles in S sub 6, and since we are multiplying permutations, the operation is function composition. And we are going to write the answer using matrix notation. So remember, when you compose 2 functions, you work from left to right. You first plug. You work from right to left. Sorry, work from right to left. You plug an input into the right permutation, take the output from that, and plug it into the left permutation. So, for example, the right cycle 5, 1, 6 sends 1 to 6. And the left cycle sends 6 to, well, 6 does not appear here, so the left cycle sends 6 to 6. The net effect is that 1 is sent to 6. We can do the same kind of calculation with 2. The right cycle, let's see, 2 does not appear in the cycle 5, 1, 6, so 2 is sent to 2. And then the left cycle sends 2 to 5. The net effect is that 2 is sent to 5. The right cycle sends 3 to 3. And then the left cycle sends 3 to 1. The net effect is that 3 is sent to 1. The right cycle sends 4 to 4, since 4 does not appear here. The left cycle sends 4 to 4. 4 is sent to 4 by the product of the two cycles. And now, working on 5, the left cycle sends 5 to 1, and then the right cycle sends 1 to 2. Doing the two cycles in succession, 5 is sent to 2. And finally, 6 is sent to 5 by the right cycle, 5 is sent to 3 by the left cycle, so 6 is sent to 3. So multiplying permutations when they're in cycle notation is pretty much the same as multiplying permutations when they are in matrix notation. Okay, so let's try multiplying two cycles and writing the answer as a cycle this time. So we're going to multiply the cycle 1562 by the cycle 156. These permutations are both in S6. Actually, that won't matter if we're writing the answer in cycle notation. So down here on this last line is where the answer is going to go, and we're going to start the answer using a cycle beginning with 1. We have to have a number to start with, and ordinarily we start with 1. Okay, we're plugging 1 into the rightmost cycle. 1 is sent to 5 by the right cycle, and now we bring the 5 over to the left cycle, and the left cycle sends 5 to 6. The effect of doing those two cycles in succession is that 1 is sent to 6. So 6 will be the next element in the answer cycle. Okay, now let's repeat with 6 to see what comes next in the answer cycle. The rightmost permutation sends 6 to 1. And now we plug 1 into the left permutation, and the left permutation sends 1 to 5. Doing the two cycles in succession, 6 is sent to 5. And now let's try 5. 5 is sent to 6 by the right permutation. The left permutation sends 6 to 2. 5 is sent to 2. And now we're going to try 2. The right permutation sends 2 to 2, since 2 does not appear there. And the left permutation sends 2 to 1. So 2 is sent to 1. 1 was the first number in the cycle, so that tells me that the first cycle in the answer, finishes here. And we are done. Every number that appears in either cycle in the original problem appears here in the answer. Now let's look at the inverse of an element of S5 when the element is in cycle notation. What is the inverse of the cycle 1325? Well, remember, in S5, the identity element is the permutation that sends each number to itself. So here's the way you get the inverse of the cycle 1325 in S5. You write the same numbers down, but in reverse order, 5, 2, 3, 1. This is a nice, easy computation. So getting inverses of cycles is a fairly easy procedure. And in general, the inverse of the cycle A1, A2, A3, and so on through A sub k minus 1, A sub k, if you have a cycle of length k, the inverse you get by taking the cycle with the numbers in the reverse order. A sub k minus 1, and so on down to A sub 3, A sub 2, A sub 1. That was illustrated in the example in item 1 on this slide. So let's try one more example. What is the inverse of the cycle 1, 4, 6, 5, 7? We're working in S7, but according to the heading on this slide, but that's not really important if you're working entirely with cycles. How do you get the inverse? You write the numbers in the original cycle in reverse order, 7, 5, 6, 4, 1, which is pretty easy to check. If you multiply these two cycles, the first and the second, which I'm claiming is the inverse of the first, let's see, remember we're working from right to left. So what happens to 1 when you do these two cycles in succession? The leftmost cycle sends 1 to 7. The rightmost cycle sends 7 to 1. The net effect is that 1 is sent to 1. The rightmost cycle sends 2 to 2. The leftmost cycle sends 2 to 2. 2 is sent to 2. Same kind of thing happens for 3. The right cycle sends 4 to 1. The left cycle sends 1 to 4. 4 is sent to 4. And I will leave the last 3 calculations for you to do. We do end up with the identity permutation, and it's not too hard to see that if you take a cycle like 1, 4, 6, 5, 7 and get a second cycle by writing the numbers in the reverse order, that multiplying the two cycles will give you the identity permutation. And now let's look at powers of cycles. So I'm calling this permutation alpha. It's in cycle notation, it's a cycle 1, 3, 2, 5. This should be the Greek letter alpha. There we go. Much easier to edit the video as I go than to edit the video at the end. So what is alpha to the 4th, where alpha is this cycle of length 4? Well, here's a picture of alpha, and we are going to begin by calculating alpha to the 4th when you plug in the number 1. So what happens when you apply alpha 4 times in succession to the number 1, looking at the cycle notation? Applying alpha to the number 1 gives you 3. Applying alpha to 3 gives you 2. Applying alpha to 2 gives you 5. That's 3 applications of alpha. And the final application, applying alpha to 5, gives you 1. The net effect is that alpha to the 4th sends 1 to itself. Alpha to the 4th of 1 is 1. You can do the same kind of thing for any one of the other 3 numbers appearing in the cycle. Alpha applied to 3 will send 3 to 2. The second application will send 2 to 5. The third application will send 5 to 1. And the fourth application will send 1 to 3. 3 is sent to 3 by alpha to the fourth. Alpha to the fourth of n is equal to n for every number between 1 and 7. This cycle only included the numbers 1, 3, 2, and 5. For the numbers between 1 and 7 that don't appear here, for example 6, we know that alpha of 6 is 6, so applying alpha 4 times to 6 will give you 6. And in general, if you have a cycle of length k, then alpha to the k will be the identity permutation. This is another fact that makes it fairly easy to calculate with cycles, as opposed to calculating with permutations in the matrix notation. What about the inverse of a cycle, alpha of length k? Well, we have one way of writing the inverse. You can take the cycle of length k that has the same numbers as the cycle alpha, but in reverse order. But here's another way of answering that question. Alpha to the k minus 1 is the inverse of the cycle alpha, because when you multiply those two things, alpha times alpha to the k minus 1, that means you're applying alpha k times, and as we've seen, alpha to the k for a cycle of length k is the identity. And now we need to talk for a little bit about disjoint cycles. Two cycles are disjoint if they have no elements in common. For example, here are a couple of cycles in S10. Sigma, the cycle 1537, and tau, the cycle 2106. None of the numbers appearing in sigma appear in tau. Those are the conditions under which we say that the cycles are disjoint. What's really disjoint are the two sets, 1, 5, 3, and 7, and the set 2, 10, 6. Those two sets have no elements in common. The first of these sets, 1, 5, 3, 7, is the set of numbers x for which sigma of x is not equal to x. Right? For the numbers 1, 5, 3, and 7, sigma moves those numbers. The second set, 2, 10, 6, is the set of numbers y for which tau of y is not equal to y. Right? 2, 10, and 6 are the three numbers between 1 and 10 that tau moves. So technically, when you say two cycles are disjoint, you mean that these two sets are disjoint. So more precisely, we could say two cycles are disjoint in this way. Sigma and tau are disjoint if the set of x's for which sigma moves x intersect the set of y's for which tau moves y is empty. We probably won't need that careful definition, but here it is if we do. And now one thing about disjoint cycles is that they commute. In other words, if you take two disjoint cycles and multiply using function composition like we always do when we're multiplying permutations, You can multiply in either order and get the same answer. This is assuming that you have these are two cycles which are disjoint. And we could just verify that by taking these two disjoint cycles, 1, 5, 3, 7, and tau, which is 2, 4, 6. No number appearing here in sigma appears in tau, so the cycles are disjoint. And now we simply calculate sigma times tau and tau times sigma, and check that we get the same answer. There isn't much to this. I'm going to write the answer in matrix notation, and we will first look at what you get underneath the number 1 when you multiply the two cycles. Okay, starting with the top multiplication, the rightmost cycle sends 1 to 1 because 1 does not appear here, and the leftmost cycle sends 1 to 5. The net effect is that 1 is sent to 5. Doing the same calculation here in the second product, the rightmost cycle sends 1 to 5. The leftmost cycle sends 5 to 5, and here again the net effect is that 1 is sent to 5. And similarly, we can verify that doing both calculations, 2 will be sent to 4. Right? In this, in the top calculation, the rightmost cycle sends 2 to 4. The leftmost cycle sends 4 to 4. So 2 is sent to 4. And in the bottom calculation, also calculating with 4, the rightmost cycle sends 4 to 4, and the leftmost cycle sends 4 to 6. 2 is sent to 6. And I will leave it for you to do the remaining 5 calculations both ways and verify that you get the same answer. Not hard to see that this is true by looking at a few examples. When I say this, I mean the fact that disjoint cycles commute. If we wanted to actually prove that disjoint cycles commute, it would not be too hard, but we would need that careful definition of disjoint. But we're not going to do it. Let's see, one other thing to note is that any cycle of length 1, like the cycle 2 in S7, is, so what is the cycle 2 in S7? 2 is sent to 2, and every other number is sent to itself. A cycle of length 1 is the identity permutation, which we ordinarily denote by the Greek letter epsilon. And now the theorem, which I mentioned at the very beginning of the video. Every finite permutation can be written as a product of disjoint cycles. This is also true for infinite permutations, but we won't be looking at infinite permutations, so the theorem here is just stated for finite ones. This is another theorem which we're not going to prove. We are just going to look at the method for taking a permutation, like the beta in this example, and writing it as a product of disjoint cycles. Okay, so if you're going to write something as a cycle or a product of cycles, the traditional way is to start off with a cycle whose first entry is 1. So we're attempting to write beta as a product of cycles, and we're going to start with a cycle whose first entry is 1. You need a starting point. And now we use the matrix notation to compute the next entry in the cycle. 1 is sent to 2. And we use the matrix notation to find the next entry in the cycle. 2 is sent to 3. And then we use the matrix notation to find the next entry in the cycle. 3 is sent to 1. But 1 was the beginning number in the cycle, so that finishes this first cycle. And now we look for numbers that do not appear in the first cycle. 4 is the smallest number not appearing in this first cycle. So we're going to take a second cycle, start a second cycle, beginning with 4. And now use the matrix notation to determine the next number in the cycle. 4 is sent to 6. And then use the matrix notation to determine the next number. 6 is sent to 4. But the cycle began with 4. So that finishes the second cycle. And now the only number between 1 and 6 not appearing in these two cycles is 5. So we begin a third cycle with 5. We use the matrix notation to find the next element of that cycle. 5 is sent to 5. 5 was the first element, so that finishes that cycle. And remembering that any cycle of length 1 is the identity permutation, right? This cycle 5 is the neutral element. We can leave it off. So for a final answer, we have written beta as 1, 2, 3 times the cycle 4, 6, product of two disjoint cycles. Let's try another example. Let's take two non-disjoint cycles, 1, 3, 5, 4 and 1, 5, 2, and write the product as a product of disjoint cycles. Okay, so here's the two cycles that we're going to multiply, and we're going to write the product as a product of disjoint cycles. I'm going to start the first cycle in that product with 1. This is the usual procedure. And now let's see, we start with the rightmost cycle. 1 is sent to 5. And then we plug 5 into the second cycle. 5 is sent to 4. So 1 is sent to 4. And now we use the product of the two cycles to find the next element in the answer cycle. This permutation sends 4 to 4 because 4 does not appear here. And this permutation sends 4 to 1. The net effect is that 4 is sent to 1. 1 was the first element of this cycle, so that finishes the first cycle in the answer. And now we have not yet used the numbers 2 or 3 or 5, so we start a second cycle with the number 2. Let's see, 2 is sent to 1 by the rightmost cycle. The leftmost cycle sends 1 to 3. The net effect is that 2 is sent to 3. And now determining the next number in this second cycle in the answer, 3 is sent to 3 by the cycle 1, 5, 2, and the cycle 1, 3, 5, 4 sends 3 to 5. The net effect is that 3 is sent to 5. And now the leftmost cycle in the original product sends 5 to 2. The rightmost cycle sends 2 to 2. The net effect is that 5 is sent to 2, which is the first number in the cycle that we're working on, so that finishes the cycle. And we have succeeded in writing this product as a product of disjoint cycles. This is always preferable because mainly because disjoint cycles commute. They are much easier to work with. And now we want to talk for a very few minutes about transpositions. Transposition, the definition of transposition is it's a cycle of length 2. So here's one example of a transposition, the cycle 2,9. And we're working in S sub 10. So here's a fact. Every cycle can be written as a product of transpositions. And then if we use the theorem from a couple of slides ago, the theorem that says every permutation can be written as a product of disjoint cycles, we have that every permutation of a finite set can be written as a product of transpositions. Well, let's try a couple of examples. Before we do, though, one thing to notice is that this claim is that you can write a cycle as a product of transpositions, but they may not be disjoint. You may not be able to write a cycle as a product of disjoint transpositions. Okay, here's the proof, the one-line proof of the fact that every cycle can be written as a product of transpositions. And this proof simply tells us how to do it. So you take a cycle consisting of the numbers in order A1, A2, and so on through A sub r. And then here is a way of writing that as a product of transpositions. The first transposition has the last number in the cycle and the second to last number in the cycle. The second transposition in this product has the last number in the cycle and the third to last number in the cycle. And you continue this pattern until you get to the transposition consisting of the last number in the cycle and the first number in the cycle. And it's fairly easy to verify, to do the theoretical verification that this actually works. But why don't we try an example? Probably more useful. So let's take the cycle 25463, and now I'm going to follow the pattern from the proof of the theorem. The transpositions will start with 3, 6. And then 3, 4, and then 3, 5, and then 3, 2. So here I've used the pattern in given in the proof of the theorem. And now it's fairly easy to verify that doing the calculation on the left gives you doing the calculation on the right, gives you the permutation on the left. So for example, let's try calculating what happens when you plug 2 into this product of 4 transpositions. We know on the right, when you plug in the number 2, the answer is 5. That's the way the cycle notation works. So now we're going to try plugging, we know on the left, that plugging 2 in gives you 5. Now we're going to try the same calculation on the right. Okay, so plugging 2 into the first transposition gives you a 3. Plugging 3 into the second transposition gives you a 5. Plugging 5 into the third transposition, working from right to left, gives you a 5. Plugging 5 into the fourth gives you a 5. The net effect is that 2 is sent to 5. And now if we try 5. The left-hand side, the permutation described on the left-hand side, we know 5 is sent to 4. So let's see what happens on the right-hand side. Okay, so the first permutation sends 5 to 5, and then 5 to 3, and then 3 to 4, and then 4 to 4. The net effect is, of doing those 4 in succession, that 5 is sent to 4. And I will let you verify the remaining 3 calculations that would have to be done to check out this equality. Why don't we try taking a permutation in matrix form? So here is a gamma in S6, and we want to write this as a product of transpositions. Well, the first step is to write it as a product of disjoint cycles, which we did earlier in this video. We saw that gamma is the cycle 1, 2, 3 times the cycle 4, 6. And now we have a pattern for writing each of these 2 cycles as a product of transpositions. Right, 1, 1, 2, 3 would be 3, 2, 3, 1. And 4, 6 is already a transposition. So gamma is 3, 2, 3, 1 times 4, 6 as a product of transpositions. So here is a quick summary of the video. Assume that sigma is a cycle of length n, consisting of the numbers a1, a2, and so on through a sub n in that order. Well, this means that for each I between 1 and n minus 1, sigma of ai is sigma of a sub I plus 1. This simply says that for any of the first n minus 1 elements of the cycle, you get sigma of that element by taking the next element appearing in the cycle. And sigma of the last element in the cycle is the first element in the cycle. This is simply the definition of the cycle notation. And if k is not one of the numbers, a1, a2, and so on through a sub n, then sigma of k is k. We know that a cycle of length n can be written in n different ways as a cycle. We know that you can find sigma inverse by reversing the order of the numbers appearing in sigma. And here's an example. If gamma is 2, 4, 1, 3, 5, then the inverse of gamma is 5, 3, 1, 4, 2. We know that if alpha is a cycle of length k, then alpha to the k is the identity. So the cycle 2, 3, 1, 4 to the fourth would be the identity. We know that any cycle of length 1 is the identity permutation, or the neutral element. So for example, the cycle 1, 4, 2, 7 times the cycle 3 of length 1 is just the cycle 1427. We always use the operation of composition when we're dealing with permutations. So when we're dealing with permutations and we write alpha beta, we mean alpha composed with beta. We know that disjoint cycles commute. For example, the cycle 245 times the cycle 163 is the same as the cycle 163 times the cycle 245, which you can verify. We know that every permutation can be written as a product of disjoint cycles. Here's an example. If you multiply the two cycles 1453 times 2463, these are non-disjoint cycles, you can write the product as the product of these two disjoint cycles, 146, 253, which I will also leave for you to verify.